high irrigation after a wet year, but we avoid some of the shocks, which is probably favorable. So thinking about this again in a more general theoretical, abstracting away a little bit, let's try to understand why this is happening. If we look at a simple model in which irrigated area is some fraction of the amount of water left in the aquifer, so this is like the bottom of the aquifer, this is the actual water table. So we are able to irrigate a certain fraction of that delta, which says how much water we're actually able to extract from the aquifer in a given year. Delta measures, for example, how many wells we have, what's the extent of the energy supplied, how much water we are able to suck every year. And when we couple that with a water budget equation, we get a kind of stochastic dynamics of the complete system. It's stochastic because rainfall is a random variable that varies from year to year. And what's interesting about shallow hard rock aquifers is this stochastic dynamic converges to a steady state pretty rapidly. The steady state is actually, in a stochastic dynamic setting, steady state is a distribution over the water table. It's a distribution, probability distribution over how much area we can irrigate. And that distribution describes well the long-term variability, the long-term distribution of irrigated area. So let's look at an example. We test this idea. I'm sorry I'm going through the slide a little bit differently because it's not the file. No, it's my mistake. So I just want to show you an example. We test this kind of model in different settings. Some of them we can solve in closed form solutions. Some of them, which are a little more sophisticated, require numerical simulation. But this is an example of what we find. So basically what happens, here's a model where the variability of rainfall is 1/2, where the mean rainfall is 1/2 and the variability is 0.25. And what happens, we ask what happens as we increase our pumping capacity, how much water we can withdraw from the aquifer every year. So as we increase, and look, please just concentrate on the right-hand plot here. As we increase delta, we are able to, the blue line represents what is the average long-term irrigated area. So obviously we increase it as we increase our pumping capacity. But what's interesting is that in the long term, this panel represents a model in which there is no discharge out of the system. So in the long term, the amount of irrigated area, the average, cannot really go above 1/2, which is the average recharge from rain. Because if you think about it, if there's no discharge out of the system, the long-term average is constrained by how much recharge there is from water, right? So we cannot exceed it. And what's more interesting is as soon as our pumping capacity exceeds the average recharge rate, it basically flattens out. So as soon as we pass this threshold, we don't really gain much from increasing our pumping capacity because we cannot exceed this line. However, what is changing is the variability. The green line represents the standard deviation of irrigated area as a function of the pumping capacity. And this keeps increasing. Now this is very intuitive to understand. Suppose that we have a very wet year, so there's a lot of recharge. If our extraction capacity is rather low, we can only take a fraction of that out in that year. So some water is left in the aquifer, and even if the recharge in the next year is quite low, there's still enough water left so we can keep withdrawing a similar amount of water. But obviously, if our extraction capacity is high, what will happen is we'll take everything out after a good recharge, leave very little in the aquifer. So then we expose ourselves to the risk that if the next year is kind of dry and there's not much recharge, we are very constrained by how much water we can withdraw. So there'll be more variability even though the mean will not change. But if we go back to here, and now we run the same simulation when there is some discharge, natural discharge out of the system, we see that now, I mean, it's maybe not so visible, but you see that the blue line now keeps increasing more after we cross the natural recharge limit. And the intuition here is that if there is natural discharge out of the system, there is value in increasing our pumping capacity. Because this time, if we leave more in the aquifer and do not take it out, some of that water will be lost in natural discharge. So if we increase our pumping capacity, we do have returns in terms of the average recharge. We lose less to natural discharge. So in this kind of setting, there is more increase both in the mean. Of course, the variability still rises for the same reason, but the mean also still rises. So in this model, when there is no discharge, there really is no point in going any further, in investing any further in pumping capacity beyond this line. But in this sense, in this case, there will be some benefit in that. Now, the actual balance here, there's a trade-off here between how much we want to invest in extraction capacity and how much we want in, sorry, there is a balance here between gains to the mean and losses from an increase in variability. And the socially optimal outcome is a balance between those two. So in order to really make a decision on the social optimum, we need to really know what is the net rate of natural discharge of the system, and then it's a matter of economic theory to balance these two and to reach a social optimum. In closing, let me just say that even if we know what the optimal policy should be, and this is a matter of more research into understanding recharge rates in this area, it will be hard to realize in this particular area the socially optimal policy because it is not the government that manages the groundwater resource. In fact, what's happening in this area is not only is the aquifer a common resource, but energy for pumping is provided at zero cost by the government. And because of that, farmers always struggle to grab as much of the water as they can and overinvest in wells, in energy extraction, etc. So it's very hard to actually reach the optimal policy because of the effect known in economic theory as the tragedy of the commons. And one policy tool that the government can try to employ trying to control that is to limit the energy supply. Even though it's free of cost, then the government could try to limit the energy supply, especially following a wet year. This would benefit everybody, because of the argument that was presented, but requires coordinated action, requires government intervention. So let me close on that. I'll just show you that this is still an important issue in the state. This recent monsoon, as you know, was very problematic. It came very late. And even in this highly irrigated area, the state was really suffering the consequences of the monsoon despite of irrigation potential that exists there. So let me close here.